leadership of the 21st Century Power Partnership, and also the colleagues from NREL, Jeff and Doug and the others. I think it's important to notice that everything started from the activity we made last year. We were working together, all the work streams of CEM related to the power system. We're working together and making like a report on the fast decarbonization of power system. That was really important to gather together and to collect all the important information. At that time, we also organized in Pittsburgh a nice roundtable where it was important to be there, also to highlight which are the main topics we have to consider. It's also important to say that this event put the basis for a few countries and jurisdictions, let's say, to plan for the action plan for the decarbonization of their system. So they are going to develop and publish before GOA their action plan. The action plan will be available. And I think this is a workshop that could facilitate those jurisdictions. I try to remember that is Australia, Chile, European Commission, India, and the UK in finalizing their action plan. So there are in the pipeline 3 workshops. This is the first one. Thank you for Brazil to host it today. So it's a pleasure to be here in Rio. And then the second one will be in Mumbai, and then there will be another one online. So all these workshops will facilitate those countries to prepare for their action plan, to make it clear which are the main action toward the decarbonization of the system. So I'm glad to say that we have also a nice keynote from our Brazilian colleagues, Mario, and also from NREL. We will also today tackle 2 important aspects. One, how to use at best our existing transmission system by using new technology, new solution, but also how to make a good planning in order to secure the massive renewables that we need for decarbonizing our system. So I think I have all the interest to say that this will be a very interesting workshop. So without any further ado, I would like to give the floor to Mario to tell us what is now important for the existing grid to be modernized. Thank you. All the best.
Hello? Hello? Yep. Okay. Well, good morning. It's a real pleasure to be here. Thank you for the organizers for the invitation to present a little bit of the work that's being done on flexibility resources for Brazil and other countries. My name is Mario Pereira. I work in a company called PSR. PSR is celebrating its 35th year. We jointly developed planning models, but we also work in consulting, and we have a strong activity in academic and research. PSR now has 125 people. We have 25 PhDs, something like 35 people with master's degrees. And as I mentioned, we both do the consulting and model development, but also work in the academic area. I myself, I'm elected member of U.S. National Academy of Engineering, Brazilian Academy of Sciences, IEEE Fellow, and this type of thing. This is just a survey of recent projects in applying our models in different countries in the world. One thing that's interesting, it's related to this presentation here. We're right now carrying out decarbonization studies for 18 countries in the Latin America and the Caribbean, and they involve the usual things, insertion of renewables, managing flexibility and storage, and also the question of transmission. I'll start with the flexibility. One of the first projects when we started dealing with the flexibility was a project with for the government of Chile. Was a competition sponsored by the Generators Association of Chile, and the idea was to see what would be the economic expansion of Chile in the next 25 years. So basically, the idea was to have, you have candidates, you have thermal plants, you have hydro plants, you have wind and solar and so on, and you want to find the optimal expansion plan, optimal economic expansion plan. This is the basic methodology. You have a module in which the module, the yellow module is kind of the planner. It solves a mixed integer programming problem and decides on a trial expansion plan, which we present by X. The candidate expansion plan is then you go to the operation model. The operation model is a detailed stochastic optimization model that does the optimal management of reservoirs, has hourly resolution, represents transmission, and calculates the operation costs. So from the yellow module, you got the CapEx investment costs. From the blue module, you got the operation cost, and the objective is to minimize the sum of investment plus operation cost. And you also have a criterion to know if your plan is optimal, okay? And if it's not, you give a feedback and you find another plan. This technique is called band decomposition. It's very well known, very robust. We have applied it to dozens of countries. And the nice thing is that you have upper bounds and lower bounds, so you can be sure that you get the global optimal. And this is just the usual candidates, as I mentioned. There were thermal plants, there were storage, there was the wind and solar. And one interesting thing is that we have to prepare the candidates and the scenarios. Different from, for example, thermal plants, which are generic, okay? We say that wind and solar, they have to have name and surname because they're much more site defined. So we use the global models for reanalysis. We get hourly scenarios for wind, we get hourly scenarios for solar, both for existing and for the candidate plants. And we also have the stochastic modeling of the inflows using a weekly resolution. One interesting thing is that there are a lot of complementarities. There is complementarity, the obvious complementarity. For example, in Chile and Brazil, the wind blows much harder at nights. We joke that are Bohemian wind plants, which combines well with the solar plants, okay? There are also seasonal complementarities. For example, wind production in Brazil in the Northeast is very strong by luck during the dry season of hydro. So there is a lot of synergy. And there is also a spatial correlation, both in Chile, Brazil, and other countries. For example, there are negative correlations between wind and hydro, which is negative spatial correlation because it helps the portfolio effects. And there are also positive correlations. So you try to capture all of this diversity in the stochastic scenarios. And of course, you have the candidates, batteries, reservoirs. In our case, we got pump storage for storage. And this is the results of the expansion. The expansion showed massive penetration of renewables. The Chilean government was very happy because the percentage of renewables in 2030 was already 75%, which was their target for 2050. And basically with the solar, Chile has fantastic solar because of the Atacama Desert. And so there was a very strong penetration of solar. And of course, when you have non-dispatchable resources such as solar and wind, this is the profile for a typical day in April 2021. This is April 2025. You see the wind penetration, the solar penetration. And we get to the problem that we have a lot of non-dispatchable resources in the system. And the way we see this is the usual way. We get the net load, so that is the actual loads, minus the generation from the non-dispatchable resources, and we got the duck curve. So how we handle the variability, how we handle the duck curve in that system. And in addition to flexibility resources such as storage, a key feature was dynamic probabilistic reserve. Basically, it's a technique to calculate the reserve you needed in the system. That is a function of the portfolio of renewables you have built. So it's a dynamic thing. For each candidate plan, you automatically calculate how much you need in terms of reserve. It's probabilistic, takes into account all the uncertainty of the scenarios. It is dynamic because it changes from hour to hour. So this became a part of the optimization, the co-optimization. So we, as I mentioned in the beginning, we wanted to minimize investment costs plus expected operation costs. Now we want to minimize the investment cost plus the cost of reserves plus the operation costs in the system, and also the reliability. So this is the definition of the actual model that was used. So it's a co-optimization of investment, operation costs, and reserves. And it still uses the same idea of Bender's decomposition. So the yellow module is the one I mentioned before with investment. Now the candidate plan goes to the operation module, and we get the operation cost, but also goes to the probabilistic dynamic reserve, which is a linear programming model that returns how much I must have from reserve, and goes to a supply reliability model that carries out Monte Carlo simulation for equipment outage and this type of thing. So you end up by co-optimizing all of the resources. And one interesting thing is that it started to capture one of the problems that we have is that suppose that you have a good place for winds that has a capacity factor of 44%. Then another good place for wind that has a capacity factor of 43%, okay? This is typical capacity factors, for example, for Northeast region. The model, if the model doesn't know about reserve, it would go and build all the winds on the 45%, okay? But if it does that, the variability is much higher because everybody is in the same region. So the reserve cost becomes higher. So the model decides, oh no, it's nice to have a portfolio effect. So it starts building the 43% or 42% if the spatial correlation. So you start to capture this. And the other thing is nice, which the investors in Chile were not too thrilled about, is that we can determine who is guilty of the reserve. So if it's the solar, is this wind and type of thing, or it's even the variability of the demand itself. So there was a way to charge the additional costs caused by the renewables in the system. We have been using this co-optimization of investment, reserve, operation, and reliability in several studies. In particular, a few years ago, there was a very comprehensive study for Brazil called Energy Systems of the Future, in which we repeated this idea of having the optimal expansion, okay, optimal economic expansion, but take into account everything, take into account generation, reliability, reinforcement transmission, stability, inertia, everything. So to get a really comprehensive analysis, this was sponsored by the German agency GIZ, and was done for EPE and the National System Operator as the main clients. It was a project that was a very strong cooperation between the agencies, and the result was pretty much the same. Brazil could have practically 100% economic expansion of renewables, okay? That with our hydro, we could have as gigantic water batteries. And also because in Brazil, originally, hydro was spread out in 11 major areas in the country because of the portfolio effects. We already had the gigantic water batteries in place, and we had a very robust transmission system, because that's our inheritance from our times in which we're 100% hydro. We have a very robust transmission system. We have the reservoir storage. So it was really easy and economic to insert, first biomass, then wind, and now we're doing a lot of solar in the system. Now, back. Now transmission, okay? When I present slides to a lot of friends in Europe and in the US, they kind of get envy because we built transmission like crazy, okay? In the past 6 years, we built 35,000 kilometers of high voltage transmission. And Brazil has one single network. Just as a reference, Brazil is about the same size as continental United States, but half Alaska, okay? The Amazon region you see there is half the United States, exactly half the United States, okay? So it's a pretty big country in terms of the range of the transmission system. Or see another way, the south of Brazil is Lisbon, the north of Brazil is Moscow, okay? So I think in terms of, and because we go this way, we have lots of climates, and the transmission system is one that actually has allowed us historically and now to aggregate both the existing hydro and now the new renewables. So the renewables in Brazil from the beginning were very competitive. We never needed to have incentives because the infrastructure we had allowed us very easily to put the biomass, to put the wind, and to put solar. But still, we have to build a lot of transmission. And the question is that in the past, for example, it would take 6 years to build a hydro plant. It would take 3 years to build the transmission, which means that I could plan the hydro and then build the transmission system and kind of customize. Now things are much more complicated because I can build renewables very quickly. So I have the problem that, first of all, I have always to be running after the renewables. And the second thing is that renewables are popping up everywhere. So the power flows in the system get very different. So you start having overloads in lines in which from the beginning you have no problems. You start having areas in which you have need for voltage support and so on. And so that's a question of flexibility. Because if I build a huge transmission line, as we are used to, this means a capex that gets there, but it may be possible that the line will be underutilized because a new renewable appeared everywhere. So how can we make our transmission system more flexible? And this was the topic of a study that was sponsored by the Colombian ISA. ISA is the owner of the transmission assets in São Paulo region in Brazil. It's also in Peru and many other countries. So ISA started a project in which we ourselves and 2 associated companies, we carried out with a straight cooperation with EP. And the idea was, what is the benefit, was the worth of flexibility resources for transmission? And the study was very comprehensive, included, I'm sorry, there was some text in Portuguese, but included energy, actively linearized power flows. It includes steady state voltage, okay, with AC power flow, and also included complete dynamical simulation, which, because Brazil has these long transmission lines and all transfer from different areas of the country, is a key problem. Because of time limitation, I'll only talk about level 1, which is active power flow. And basically, the idea is that it's the same methodology I mentioned to you, which is I'm going to carry out an optimal integrated expansion of generation and transmission. In this case, the study asks that we start with an expansion plan. And that because this would allow us to look better the benefits of the traditional transmission, business as usual transmission, compared with the flexible. So basically, we carried out 2 studies. So one study with business as usual transmission, another study with the flexible resources, and figured out what was the economic benefit overall in terms of cost. Okay. And so which are flexibility resources? Basically, FACT, Flexibility Transmission System. There were a company called SmartWire that basically you have the ability to change the impedance of the lines and change the flows. We have batteries, so we have a dynamic line rating, and the other resource was flexibility aggregators. Basically, we imagined that at the distribution level, there would be flexibility aggregators. In Brazil, for example, we have a very strong amounts now of distributed generation, something like 20,000 megawatts of solar at the distribution level, which means that there is a lot of variability at the net distribution loads and a lot of interest in having flexibility aggregators in the system. So we made the hypothesis that there would be flexibility aggregator on services, and these services would be hired by the main transmission grid to serve as a flexibility resource. And so that's the system. So it says installed capacity 190 gigawatts, about 300 hydro plants, 200 large thermal plants, 3,600 renewable farms. That's the high voltage. I'm not talking about the distributed generation, which 12,000 buses and 18,000 circuits. And so that's the traditional. We do a power flow analysis. We identify regions in which you have overloads or region that would be a benefit to expand the system. And one thing that people don't mention a lot, but it's critical, is how do you create candidates, okay? people like the optimization model in which you have lots of candidates, but creating candidates is a headache because you have to do all the environmental studies and have to do the costing. So we created automatic model to do this called Pathfinder that you define, well, you want to go from region A to region B. It finds the least cost expansion, take into account all the layers, for example, environmentally sensitive areas and all the topography and this type of thing. So it helped us automate the process of creating candidates because it's another point of flexibility because there is, again, a very large number. The official studies take a long time, so this helped us make the process richer in terms of possibilities. And another thing which is was a challenge is, for example, batteries. I have 12,000 buses, so I can put batteries everywhere. So how do I screen the batteries? So what we do is the following. We do a stochastic simulation with our resolution. So for each bus of the system, I have spot prices, okay? Then I do an analysis, okay, if I put a battery here, marginal battery here, how much money the battery would make by doing arbitrage on spot prices, and also how the battery would make money working as a resource, as a reserve. So the batteries choose whether they work as providing energy, whether they work as a reserve, and I get the final revenue of that battery of that size at that place, okay? Then I repeat the process for hundreds and thousands of buses. This is processing, it's done in parallel, and I get a cost benefit. So I divide by the capex of the battery, and I get a benefit cost index, okay? So I screen the ones that are lousy, I get the ones that look interesting, and then these became candidates for the actual planning study in which you actually build or don't build a battery and see the effects. So for that study, for example, we ended up, we screened thousands, we ended up by 80 candidate batteries, and they were located in these places here. And the range going from lighter to darker indicates, better benefit cost ratios in the system, okay? We do the same screening. Of course, it's called BAT screen, okay? We actually have BAT screen, sun screen, wind screen, and we have fact screen, okay? And we do the same for the flexible AC transmission systems. We imagine that we have all of these fact devices everywhere. We calculate their marginal benefits and how much money they would make, and divide by their capex and get indices, okay? So we end up with a set of conventional candidates, which is on the left, is the one I had shown before. We do this by looking at, places where you need reinforcement, overload, and so on. And we get on the right a set of flexibility candidates. As I mentioned, we then run two studies, a study with the conventional candidates, a study with the conventional plus flexibility candidates. And we get what is the lowest cost expansion. One thing that's very interesting is dynamic line rating, okay? Because what has happened is that as all of you know, people are very conservative when they calculate the transmission line limits. They basically imagine that temperature is horrible and it's not the wind's not blowing at all. But this maybe is just happens 1% of the time. Okay, if I can actually now I have ways of knowing the temperature, the winds in each segment of the transmission system. So the idea is that we have scenarios of temperature, we have scenarios of wind, which we already had because we use this to calculate and we divided the country into lots of little squares. And we have a calculation then, we have the formula for calculating the transmission line capacity. So for each stage, for each hour, for each scenario, we have the actual loading capability of all the transmission lines. And I'll show you one example. It's very interesting. The red one is the official transmission limit, okay? And the gray one is how much you can actually go. So there's a lot of fats that you can take advantage of. And this helps because, for example, there are lots of regions in which you have wind and you have this temperature. So is another thing that is very attractive to do. So this is the comparison. There's a lot of details. The reports are going to be released soon. So, but basically, for you to have an idea, the convention, you see that the big difference between conventional and flexible is that we avoided building the sequence of transmission lines in the middle, okay? So there was a huge saving because we're able to use the other resources to avoid needing those transmission reinforcements. And basically, the conclusion is that we already have excellent experience with flexibility resources for generation interconnections, such as storage and especially dynamic line rating. Dynamic probabilistic reserve. And now the experience with the flexibility resources for transmission has been very positive. As I mentioned, we've done this for Brazil, for Colombia, and for Peru, and was very nice because ISA made available their experts because they own the transmission system in these countries. So they made available their actual engineers. So there's a lot of collaboration with people that had actually experience. PSR had done studies in all of these countries. So, and I think that also with the collaboration with EPE, we have provided EPE with the planning tools I had mentioned. So also the interaction with VE was very productive, not only because they're experts, but because we share the tools and this type of thing. So I think that this is something that has a lot of future, and it's going to be instrumental in ensuring that we have a fully renewable, clean insertion in the system. Thank you very much.
Jeff, do you want?
I think we'll take some questions if we have any at the end. We have one more presentation to go, and appreciate if you can just be patient for a moment. Thank you.
Sure. Thank you, Jeff. And thank you again, Mario. That was a very insightful presentation. It'll be quite difficult for us to follow, but my name is Prateek Joshi. I'm a researcher at the National Renewable Energy Lab. I'm here with my colleague, Desai, and hopefully we will build on that presentation and focus on a little bit more on transmission planning, and specifically this idea of using renewable energy zones for transmission planning. So last year in the collaborative report that the CEM Power workstreams put together, one of the key takeaways for the ministers was coordinating the renewable energy and transmission planning. And one way to do that is with renewable energy zones. And so I'll start with an overview of what that is, what that process looks like, highlight some case studies from around the world, and then Jal will conclude with a discussion on some of those key enablers from the perspective of the Clean Energy Solutions Center. And so, as you can all guess, the foundational requirement of a renewable energy zone, or RES as it's commonly abbreviated, is the high quality renewable energy resources. For instance, places with really good solar irradiance or wind speed. Then on top of that, we need to ensure suitable topography exclusions. So that's just a fancy way of saying we need to make sure that we can actually build on this land, that it is not an protected environmental area or a city or a water body, things like that. And then when we know where our good renewable resources are in the country or region and where the suitable land is, we can look for that missing ingredient for a RES, which is the strong commercial interest. So are the developers actually interested and willing to build on this land? I think this can be the trickiest to gauge. It can vary the most widely among the case studies, but some examples I have listed are whether there are economic development areas designated by the government. People have conducted surveys of developers, looked at leasing activity. And then all of this adds up to candidates for renewable energy zones that can then be fed into different transmission planning processes. And so the RES transmission planning process, it's been applied in several different places thus far. It's a proactive method to plan, approve, and build transmission that connects high-quality, large-scale renewables to the power system. So I think Mario is right in saying, at least we in the US are very envious about how Brazil has been able to build transmission so quickly. We have a lot more issues with that. And so I'll dive into that a bit more later, but this can help us overcome some of those barriers. So several years ago, some of our colleagues at NREL developed a guidebook for this process, and they included 6 suggested steps in this framework. The first one is just thinking, what is the overall aim of this RES planning? What technologies are we going to include? What land are we going to exclude? And then it's bringing together these different stakeholders to make those decisions. Next step is assessing your renewable resource and then selecting your candidate zones based on those resources, but also based on the land type and the commercial interest. So the culmination of these first 3 steps, I've shown it here for the US state of Texas. I'll come back to this a little more later, but Texas was the pioneer of this process and really set an example. And so this figure in red is showing you the candidate zones that they identified many years ago when conducting this process. And so then the next 3 steps listed here focus on the transmission. So step 4 involves looking at the different options for building out transmission from the existing grid and load centers to these different zones or connecting the zones to each other. That can have different costs and benefits that are weighed. And then finally, a transmission plan can be designated, based on those options. And then the last step is to actually build the transmission, which of course, easier said than done for places, but clearly Brazil has been able to do a great job of building out that transmission. And so these final 3 steps I've shown in this figure for Texas. So you can see this is their transmission expansion plan. Most of the population in Texas and the electricity demand is located in this eastern region. And so they designated a plan to build out transmission to the wind resources in the west. So you can see how some of these candidate zones have been connected. And we're talking about this today because traditional transmission planning might miss the best resources due to 2 main barriers, the circular dilemma or timescale misalignment, which I'll talk about. So the circular dilemma is this concept that is conveyed in this figure. Essentially, first, the developer of renewable energy needs financing, but then the financiers, the banks, they want to see that transmission is available so that the renewable power plant will actually be able to sell its power and recover its costs. But the transmission often needs regulatory approval, and those regulators, as part of their own due diligence, want to know that a power plant will actually use this transmission, so it'll be so-called used and useful. But then those generators, again, need financing, and you could see how this can become, in some instances, a difficult cycle to break. And then the next one here is the timescale misalignment. So maybe a renewable power plant could take just a couple years to build, sometimes longer now due to some interconnection backlog issues in some parts of the world. And then transmission, at least in the US, it can take quite a long time to build, 1 or 2 decades at worst. And so coordinating the 2 can be difficult in some places because of the different timescales. So the goal of this is to proactively coordinate or co-optimize, as Mario mentioned, the generation and transmission expansion. And so for these case studies, just because we don't have time to go into depth in a lot of them, I'm just going to highlight a few key points just so you can see how this has been implemented in practice as opposed to just a theoretical discussion. So I'll start alphabetically with Australia. So Australia, the Australian Energy Market Operator, or AEMO, every couple of years comes out with an integrated system plan where they talk about different potential renewable energy zones in the country. And what I find particularly interesting about their approach is that they categorize their zones into different buckets, and they take this phased approach that I think is quite useful. So they identify zones that are currently in development. They identify zones that are in the process of getting regulatory approval. And then they identify future projects where they say, okay, we need more studies for this. They also include 6 offshore wind zones, and then within the zones they've identified, they say this is our potential solar resource, our wind resource, but they also account for those battery storage needs, and then pump storage hydro as well. India in 2017 concluded the Ministry of Power worked with Lawrence Berkeley Lab in the US to conduct a study looking at potential zones in their country. So they identified the zones looking at resources and land availability and land use, like I discussed. But they did something interesting for the zones. They calculated the attributes of zones. They looked at multiple criteria, and the study does a nice job of diving into that methodology. So they looked at things like population density, slope, levelized cost of electricity, and then they assigned weights to those attributes. So they said, maybe this attribute we think is more important, another attribute we think is less important, and that allowed them to basically rank these zones and have another way to prioritize where they should develop first when meeting their renewable energy targets. And so just last year, there was an exciting bit of news. India announced plans to build transmission to connect 66.5 gigawatts of capacity in some of these zones. Last year, NREL and 21 CPP were very involved in a clean energy report for Mexico, which talked about a variety of things, characterized renewable energy resources, but also included some key findings relevant to renewable energy zones. So they found the geographic diversity of renewables all throughout the country could reduce the integration costs. And then in red here are some transmission hubs that have been identified that could connect to the high quality wind, solar, and then they also looked at geothermal and hydropower. And then the authors of that study noted that the zones or hubs located both at the northern border with the US and then the southern border with Mexico could also provide economic opportunities for Mexico through exporting this clean power as well. So New Zealand is currently in the middle of a RES process. They're calling this a national consultation. So they're doing a lot of stakeholder engagement, a lot of public outreach. And so in addition to identifying potential zones shown in green, they're also looking at coordinating future demand. And that's shown in blue is what they're calling industrial clusters, where they're thinking we can have large electricity users, such as manufacturing facilities, located or concentrated in these areas to then take advantage of the renewable energy zones as well. So it's also an interesting approach of not only coordinating supply and transmission planning, but also thinking about demand as well and integrating that into the system planning. And they've identified this Northland region as a pilot project that they're hoping to commence soon. So that'll be a good one to track in the near future. NREL has been really involved in transition planning in the Philippines. So this started several years ago with the grid integration study that looked at how the Philippines could integrate between 30 and 50% of wind and solar by 2030. And one of the key recommendations of that report was to look at renewable energy zones in the country to help with transmission expansion to meet those renewable energy targets. The main thing I want to highlight for the Philippines is just how extensive and collaborative the stakeholder engagement was. And so this figure is showing you this really big org chart here. They had a very clearly defined institutional structure with a chair, a technical advisory committee, 2 different working groups, and then a large list of stakeholders. So I thought this is a a great example of the entire RES process, but I just wanted to highlight the stakeholder engagement for the Philippines. So second to last one, I think here is South Africa. In 2018, the government identified 8 renewable energy development zones in the country and then identified 3 more in 2021. And then those notices, what I found useful about them was they included a procedure for environmental permit applications for developers to build in these zones, which I think that upfront clarity is quite helpful in this. And then you could see the 11 zones here. To connect these zones together, they identified strategic transmission corridors, which are shown in this insert at the top. And so that's where they're basically prioritizing building transmission to connect to these development zones. And then the last one here is for the US. I already talked about Texas and how they pioneered this in the mid-2000s, and they were just looking at wind. Then a couple of years later, around the 2008 to 2013 timeframe, the western interconnection of the US, including parts of Canada and Mexico, were looking at renewable energy zones for the entire region. And in addition to wind, they also looked at solar PV, hydropower, and geothermal. And then the US is currently in this process of a national transmission plan study supported by the Department of Energy. And a component of that study includes looking at interregional renewable energy zones. So not just one region of the country, but the entire continental US, looking at hubs for wind and solar to help inform transmission planning. So yeah, so that wraps up a very rapid fire round of case studies. And I'm happy to go further in Q&A, or we can talk about this over lunch as well. And right now I'll pass it over to my colleague Jal to conclude with some of the key enablers and to also talk about the Solution Center.
Thanks, Prateek. So today I'll be talking about the key enablers of renewable energy zone transmission planning. So we have got 4 enablers. So the first one is process clarity, right? So one, outline clear and transparent processes for res designation, selection, and build out, as shown in the flow chart in the earlier slide. The second one is strong stakeholder engagement, right? This is one of the key enablers, right? So when you plan or develop any energy infrastructure, it is and should be a stakeholder-driven process informed by decision-making tools and a framework. So in this case, you want to engage all of the relevant stakeholders, including private developers, landowners, government ministries, environmental advocacy groups, and other groups. The third key enabler is high quality data. As Prateek was mentioning in his slide, right? Like the first step or the initial step for res designation is resource potential. And to do that, you need to have high quality data. So that's why that is one of the other key enablers. And last but not the least is the regulatory weight, right? So you want to ensure that the res transmission process ultimately feeds into the regulatory process to build transmission projects. So overall, a proactive transmission planning that successfully integrates renewable energy zones would help deploy larger renewable and would help and assist energy planners with the climate change mitigation goals. Now, let me talk about the Clean Energy Solution Center. So this is one of the work streams of Clean Energy Ministerial. And we help government organizations, policy, and analysts to frame programs and policy to deploy clean energy solutions. So we have 3 services. So first one is Ask an Expert, right? We have 80 experts around the world, and then based on the requests that we receive, we do the matchmaking process. And we have received several requests that we have completed on this topic area. And the impact reports are on our website, so please do check it out. The second service that we offer is training and peer-to-peer learning, right? So we do series of webinars. So in partnership with USAID and other Greening the Grid and other partner organization, we have conducted series of webinars. And again, that's uploaded on our website. So again, do check it out. And the last one is resource library. So we have policy briefs, reports, and documents that we host. So again, if you want to look into this topic, that's the place to go. Now I'll hand it over to Jeff, close the session, and we welcome questions.
Thank you very much, Jal. And please, let's give these two groups of presenters a round of applause. I think they were really very nice presentations and very complimentary, I think. I'm going to open it up to questions now, but I would like to take the first one myself since I have the microphone. And it's to Jal, I guess. And so if a country wants to do a renewable energy zone, but it doesn't have high quality data and doesn't really know where to start, is that something that, I mean, what should they do in that case?
Oh. Yeah, so that's the perfect example for ask an expert request, right? So we have a portal, they can reach out and submit the request on the portal, or they can reach out to me directly. And then we have got few experts, basically, like you all, right? And then we would do the matchmaking process, and then we'll complete that analysis for them.
Okay, great. Thank you. For those online watching virtually, please raise your hand if you have any questions that you would like to ask. I see there's something in the chat already. We have a first question back here. I'll bring the mic to you.
Thank you, and thank you for the presentation. I'm seeing how energy planning is becoming more and more complex, not just because of batteries, because of multiple options that you can simulate. I was wondering if you have experience simulating adding to the energy planning, green hydrogen, or coupling with other sectors, demand side management. And that would be one question. And the other is, if now that countries have more ambitious targets for renewable energy, is it going to change the way we do energy planning? You know, for example, if country want to do 100% renewable energy, what does it mean to set the target and then to see the way that we're going to achieve that?
Okay. First, excellent question about renewable targets. We have just carried out a study for the World Bank in the case of Brazil, in which they asked us to answer the following questions: how much would it cost to have 100% renewable, 100% zero emission Brazilian system? And so we did the study in 4 phases. Phase 1, business as usual, a reference that is. Take into account that you could build thermal plants, whatever. Phase 2, we would get zero emission. And the way we did this was to retire all the existing thermal plants at the end of their contracts. So there was no big money to be paid. And because the target was 2050, all of the thermal plants in Brazil could retire at that point, and then put a constraint that no more emission. And then we calculate the difference between this expansion plan with the other, and the difference was very small, okay? And the reason is that in Brazil, already it's very competitive to have clean energy. Then the third point was, what about electrification of the other areas of the country? Just as a reference, I think the average energy loads today would be 60,000 average megawatts. The target would be 100,000 average megawatts, and electrification would be another 60,000 megawatts. So we would go from 60,000 to 180,000 average megawatts. So we did the study, and we showed that it would still be possible to have completely clean expansion. Take into account, as I mentioned, all the problems, stability, and this type of thing. And then the next step was, what about climate change, okay? And climate change would affect, for example, the distribution of hydro, and this would affect. And then the scenario was that if we generate the climate change scenarios, and so if there is a climate change, we're going to build reinforcements to the system to compensate the lack of, but still was possible. So for each case, we get green premium. And for example, a huge part of the expansion was related to green hydrogen. And as you know, in the case of Brazil, we both could have, there was a lot of interest. We've been doing a lot of studies in green hydrogen. And for exporting for Europe, for example, in the new directives, you could either have dedicated renewable plants, or you could get from the grids, given that you can show that your grid is 90% clean, which we would, the modeling of the hydrogen would be, you have this, you have a target to production of hydrogen, you can either buy from the grids, or you can build your dedicated renewables, and you can put storage, because if you want more fixed production, storage could be batteries, or storage could be pumped storage. Pumped storage is a very important thing and a promising thing in Brazil. The same thing has been with the studies for Colombia and other countries. So I think that's the way to go. And if you allow me just one small compliment, I think that what also makes planning very challenging is distributed generation, because I cannot control the people who are going to build the distributed generation, solar panels, and so on. So for EPE, we developed a technique for calculating the net loads. It's something like you start with a guess about the insertion of renewable generation, then you do the expansion plan, assuming that there is this renewable, the distributed generation, and then you get all the long-run expansion costs, this kind of thing. Then you go back to distribution and evaluate if people would change their decision to build, depending on incentives and this type of thing, get a new net loads, and go back to the planning. And amazingly, the thing converges, and they can show that this converges to equilibrium. So I think that the challenge of having discos and other decision makers is also makes the system more complex, but there are tools for that. Sorry for long answer.
Thank you very much. I'm sensitive of the time. I realize we're standing between you and lunch, but there is one more question online, and that is from Dorival de Souza. Go ahead, please.
Okay, I'm from APE, Dorival. My question is to, I think this Prateek Joshi, I think that's the name, related to the renewable zone. You showed some renewable zone in the US, and that's my particular interest in that zone, because I haven't seen when you showed the renewable zone, the new links, HVDC link that's now is start to be built in the United States. And there was about 3 big links. For example, the Sanzia, the Transwest Express, the Grand Belt Express. This is something very new. My question is, there is now better condition to implement long and large transmission line in the West?
Yeah, so there was a question about HVDC in the US, correct? And
Yes.
yeah, I think so. For these examples of renewable energy zones for the US, I talked about the transmission expansion planning is not necessarily HVDC. So for example, for Texas or for most of the Western interconnection, it was AC, HVAC transmission lines. I do think that there's increasing interest in HVDC in the US, but I'm not sure the latest on, what those specific plans are. And I know that, it's not as big of a thing currently. So welcome any other responses to that. So yeah, essentially these renewable energy zones in the US at least are primarily AC.
Yeah, that was sorry, this is Doug Arendt, also from NREL. That was the zones you showed were inside a system operating zone of ERCOT, Texas. They were not HVDC interconnections. There's another study that's been done for HVDC interconnections across the United States. It's called the CEMS study, SEAMS. But that's just to clarify that point. I wanted to clarify and build off the last question about distributed generation, because I think it's really important to understand that there's a trade-off and between transmission build out and flexibility, operation of the transmission system, and distributed generation. And this question of how do you have visibility to distributed generation, as Mario said, is really, really important. So understanding where that might be built out. There's a set of best practice tools that have been developed and data that can be used. It also overlays very, very carefully with policy approach to that. So Brazil implemented a net metering approach. Australia did the same thing. Australia now has over an incredible amount of distributed generation, the biggest in the world in South Australia. And most importantly, the system operator has no visibility to when it comes online, except for through weather forecasting, and no ability to control it because they didn't put the rules in place at the beginning to allow those systems to be controlled via aggregation or via some market signal. And so we've learned some lessons about how to best approach distributed generation that we should also be talking about and sharing, both on the planning side, but also on the policy and market design environment that would be very valuable as well to follow up on. So thanks for that.
Thank you for those nice synthesizing thoughts to end this panel. I want to thank everyone for coming, and I hope that you all enjoy your lunch. We will try to make this recording available and put it on our website if you need to watch anything again. And we have some sheets in the back that summarize the collaborative report that we produced last year. And there's also a link to the full report, which is a collection of about 50 slides that talk about everything we've learned about decarbonizing power sectors over the past 10 years or so. So thank you again.